afternoon, everyone. Thank you very much for coming along to this afternoon session. We have Alex this afternoon in the third segment on Pipe-ifying Python.
Hello, everyone. Welcome. So we're going to talk about Pipe-ifying Python, the how and why of interpreter hacking. I'm Alex. I'm an honest student at ANU, finishing up very soon, and I have a bunch of interest in programming languages, and so I've come to share some of that with all of you. Now, there's this programming language feature that exists in a bunch of other languages, but not in Python, and it's called pipes. And I kind of want to, first of all, let's motivate this with some Python code that currently I can write. So maybe I want to say something like this. I've got a bunch of code that's going to do something. What's going to do? First, we're going to do an HTTP request. We're going to get some data out of the internet, and then we're going to take the result of that HTTP request and pass it into this base64 decode function, and that'll do some decoding of the data. Then I'll take that decode and I'll put that into the split lines function. And then finally, I'll pass that into the sort function. And so what you'll notice happening here is that the order that the code is actually executing in is the opposite way round to the way that I have to write the code. I have to write the sort first and go down. So here's an example. In Bash or any shell scripting language that you want, we write commands and we pipe them together with this vertical bar symbol. And so this is the same thing. We'll use curl, which gets something from the internet. We'll download it. We'll pipe the contents of that file into the base64 decode command. That'll do the decoding. And then finally, we'll sort it. The splitting lines happens automatically. And as you can see, compared to the Python, this comes in the order that we actually kind of want to express these operations in happening, which is pretty nice. And we also don't have all these brackets. Like in the Python version, I have all these brackets for all the function calls, and it gets pretty nested. But Bash is a special language that we use at the shell. What about a real programming language? So there's this programming language called OCaml. It's a functional programming language. I hope I'm not going to scare everyone away with this too much. But this code is going to do exactly the same thing. Except now we've got these arrows, these triangles with the greater than and the vertical bar. And now what happens is that we do the HTTP get the same, and we're going to take that result and we're going to apply it to the decode function. That's just a function. And then there's another function, the split lines function, and we're going to apply that there. And then finally, we're going to take the result of that function and put it as the input to the sorting function. And now we see there's no brackets, and also the code is going to execute in the same order that we've written it, which is kind of nice. Now, OCaml, you can also write it in the same way as Python. And it looks pretty similar to the Python code if you do the sufficient amount of renaming stuff, where we've got all these brackets, and it gets a little confusing, and it's the opposite way around. So I can see the Python code that exists on the left, and on the right, and what I really want is to be able to write Python code that looks something on the left. So here's some hypothetical syntax for a totally made-up programming language called, maybe let's call it Python. It's Python with pipes. And it's going to do the same thing as before. We want to get the HTTP request. We're going to put that into the base64 decode function, put that into the split lines function, and then finally put that into the sort function. So I really wanted this, and I really wanted this in Python specifically, because Python has a bunch of advantages over these other programming languages that I was thinking about at the time. The first is Python comes with all these amazing libraries. There's all this sort of stuff, there's ecosystem and infrastructure around writing Python code already, which I really want to be able to leverage when I'm doing stuff. I also know how to use Python. It's a programming language that I have a bunch of experience in. I've used it for many, many years. And going and learning OCaml, it's a big investment. I've learned it now, it's a good language. But at the time, I didn't want to put all this effort in just to be able to get this one tiny little incremental bit of change to the language. And the final is that I'm in uni, I have an assignment to submit, and the assignment has to be written in Python. And they're not going to be pretty happy if I'm submitting them OCaml code and they really wanted a Python submission. So what did I decide to do? I really wanted this feature, and I really needed to use Python. I decided to hack the interpreter. I'm I'm going to take the Python interpreter, and I'm going to add stuff to it myself. which you can do. Python is an open source project. It exists as a repository on GitHub under like Python/CPython. And I made my own custom fork of this. And you can do this too. You can clone the repo. You can fork the repo. I added some new lines. I modified a few things. And in total, the whole change was only plus 38 minus 2 lines of code, which I was like kind of surprised that to add this new syntactic feature in the language was actually not a dramatic change. Now, noting here that if you actually were to like look at the patch, that it says something like plus 600 lines. Most of those 600 lines are auto-generated code that gets committed. Those aren't lines of code that like I wrote. They were lines of code generated by some script. Cool. So the goal of this talk is I want to explain to you what it is that I've done and how it is that I did it. And in order to do that, we're going to have to learn a little bit about how Python works. But it turns out that in order to really understand Python, there's sort of this like broad class of programs that are very similar to Python, that have a very similar sort of structure, and understanding the theory behind interpreters is super important. So really, this is an interpreters 101 talk. But it actually turns out that the theory behind interpreters is very similar to the big scary word, compilers. Welcome to Compilers 101. You've been trapped into my miniature university lecture series. I hope you enjoy. Now, if there's one thing that I want you to get out of today, if you've never experienced compilers before or have any experience with languages and programming language development, it's that these things work in a bunch of stages. They have different processes and bits of data that they move between that represent data in the right way for the specific tasks that go into making the program run. So I've simplified it down roughly into the 4 stages that Python has. These might be slightly different for different programming languages, but the first stage is tokenizing. That's going to take in a whole bunch of like text in the form of maybe you're typing something in at the REPL or you've loaded up a file. We call that tokenizing because it's going to take all those strings and split them into a bunch of words. And then we're going to take those words and we want to structure them. We want to figure out what the grammar of the structure is, what the semantics are. And that all happens in parsing. So parsing will take these sequence of words and construct trees out of them. And then once we've parsed this data into trees, we're going to convert that into some instructions that can actually be run. And the reason we want to do this is mostly for performance, but it also helps simplify a lot of the work. And that happens in a stage called translating. So Python has this. Python doesn't compile code. Secretly, it does. It's going to take in the parse trees that we're going to construct and turn those into sequences of instructions. And they're not machine instructions that you can run, like if you've used a C compiler and that spits out like x86 opcodes or whatever. This is going to spit out instructions for the Python virtual machine. And then we finally run those in the interpreting stage. And so that's roughly everything. I'm going to go through that and see how pipes fit into this and how we can insert them and teach Python about how to read pipes. And we're going to start that off with the tokenizing stage. So here's a little program that I wrote with pipes. It's a little simpler than the one that I had before, and it shows off some of the interesting features here. What we want to happen here is to take that string high with an exclamation mark and pipe that into the length function. And the length of high with an exclamation mark is 3, so that should evaluate to 3. And then we're going to take that and check if it's equal to 3. So hopefully, if everything goes well, this should evaluate to 3. But the first step that Python needs to know is it needs to know how to split this into a bunch of words. And the first thing we see is a string. Python already knows how to handle strings, thankfully, and it handles them as individual tokens. I'm oversimplifying a little bit here, that's okay. But then immediately after that, we have our pipe. Now, currently, Python interprets that as a vertical bar and a greater than, and it sees those as 2 separate symbols. And we say, those aren't 2 separate symbols anymore. They're now going to become a single symbol called the pipe operator. But when we do that, it will now have our brand new token that'll get minted out, and it'll look something like this in the representation of the code. And then the length, that's also an identifier, and an identifier is its own token, so that comes afterwards, followed by a couple of brackets, so those are separate tokens. But much like with our pipe operator, the double equal sign is its own token. And this is how we can distinguish, like inside the compiler, between 2 equal signs that follow each other for like variable assignment versus the 2 equal signs that are right next to each other. And that's like equality checking. So that's one thing. And then finally, we have this 3, which is just a number, and that's also totally fine. Now, how does Python actually represent this tokenizing stage? Well, there's this big file. It's not that big. It's 100-ish lines, grammar/tokens, and it has a list of all the tokens. And on the left-hand side, it has the name of the token, and on the right-hand side, it has the symbol. And so we have a bunch of them, like plus and minus and star and slash. And so what we can do to add the pipe here is literally add a line down the bottom that says pipe, and then we put what the pipe symbol is. And that's tokenizing. Python now knows that if it sees these two symbols next to each other, to treat those as a pipe symbol. Awesome. Now we're going to get into sort of the meat of this. How are we actually going to parse this structure? So before we sort of understand how parsing works, we need to understand what we're parsing into. And programs inside of the compilers and interpreters like to be represented as trees. So here's a little bit of code down the bottom, length high equals 3. I've removed the pipe for now, but we're going to add it back in very soon. And the structure of this code can be represented in an entirely unambiguous way by using a syntax tree. In the syntax tree, the nodes represent like the parts of the program that get grouped together. And we see, and this sort of encodes the semantics of how we evaluate this. So we start from the bottom, and then we slowly evaluate up until we get a result. At the top, we want to like compare the equality of two things, but in order to check that they're equal, first we're going to have to call that length function on high. And so when we evaluate that, we're going to get 3, and then we're going to be checking if 3 is equal to 3, and indeed, that's true, and that's brilliant. There was no ambiguity about, like, is the high checking equals with 3, like, is it length of the equal sign? By doing parsing, we get rid of all these ambiguities in the code, so we can do analysis over it. So what we can do is, well, Python has this slightly scarier file called parser Python ASDL. ASDL is the abstract syntax description language. It is the language for describing the syntax that is abstract. So it has all of these nodes in the tree explicit as lines in this file. So it'll say, this is what an equals comparison looks like. This is what a function call looks like, et cetera, et cetera. Oh, hey, this is what a number is, hey. And so what we can do is we can add pipes to this file. And that means that now we can say, OK, we have some code on the left which has a pipe in it, and we're going to turn that into some abstract syntax tree where that pipe joins together the high and the call of the length function. And that way, the equals sign is going to get evaluated last, and we're going to evaluate the pipe part first. We've now removed the ambiguity of, like, are we piping into the 3? That doesn't really make any sense. So that's useful. But how do we actually perform this translation where we want to go from a sequence of tokens into this tree? And the actual answer behind this is a little complicated, but we're going to be using it using Python's system of using grammars. So there's this actually scary file called grammar/python.gram. And don't worry, we're going to break it down. It's going to be a little less scary very soon. And it expresses all of the rules about how we turn sequences of tokens into like trees of these grammar trees. And they sort of follow this format that I'll explain here. This is going to look a little bit arcane, but we're going to step through it slowly. It's going to be OK. On the very first line is the word comparison with a colon after it. This means that we're declaring a new rule. This is the comparison rule. This is the rule that tells Python what to do if it might see an equals sign. And so maybe you'd use something if you're like in an if statement. You're like, oh, I need to parse an if statement. After the if keyword, I expect there to potentially be a comparison there. And what does it do? It looks for the sequence of tokens, and there are two options presented here. There's a bunch more options for things like greater than and less than and whatnot. But we'll just do 2 for now. If we see an equal sign, then we'll be in the first case. And in that case, we're going to have something on the left of the equal sign and something on the right of the equal sign. And if we do see that, the thing on the left is going to be an A, and the thing on the right is going to be B, and then we'll execute the bit of code in the curly braces. And that equal thing there is going to construct the tree. So you can really think of this saying, if you see something followed by an equal sign, followed by another thing, construct the syntax tree that has the thing on the left being on the left of the equal sign and the thing on the right being on the right of the equal sign. Now, it is possible here that we might not see an equal sign. That's OK. I can say, if true or if some function call. And in that case, we're going to defer down to a different piece of syntax. And that happens in the final case, where, there's no equal sign, there's no greater than sign, that's OK. We'll just parse something else. Awesome. There's an extra thing here, which is on the left and right-hand side, and also on the final line, I've got this sum. And the sum is a different rule. That's the rule that tells us how to parse things that might be additions or subtractions. And we see here that the precedence of the operators, or like the order of evaluation of the operators, is encoded into the grammar. If I write code that is like 1 + 2 = 3, I want to make sure that I'm doing the addition before I'm checking the equality. And that's encoded in these grammars. On the left-hand side, we expect to see a sum, rather than the other way around. Like, if we're doing addition, we don't expect to see any equal signs in that. Awesome. What we're going to do is modify this rule a little bit to add pipes into it. So now instead, on the left and right-hand side of expecting to see a sum, we are going to potentially see a pipe. And then we're going to have our own rule for declaring pipes. And that's going to have something on the left of a pipe symbol and something on the right of a pipe symbol. And if we don't see a pipe, that's OK. And this means in our example where we wanted to say something equals 3, we can still see a 3 there, even though there's no pipes visible. But if we do see a pipe, we're going to construct that same syntax tree node, where on the left-hand side we'll have something, and then we'll pipe it into something on the right-hand side. Now, something that's different with the equal sign rule is on the equal sign, I had the left and right-hand sides were both sums. But here, with the pipe on the left-hand side, I have another use of the word pipe. The rule has become recursive. Now, this is super important if we want to write code with multiple pipes, one after the other in it. If I want to write some code that looks like this, so we're going to take the high and put it into the length function, and then we're going to take the length and we're going to turn it into a string, we need to make sure that these things happen in the right order. I want to pipe the high into the length before I do the result of that into the string. And so that's why we have the pipe on the left-hand side there. We want to parse the pipes all the way on the left-hand side before we do the ones on the right-hand side. And if we do that, we're going to get this slightly larger syntax tree, and you'll see that the bigger outer pipe only has smaller pipes on the left-hand side. And we can check that this makes sense by evaluating it, just like we did earlier with the example without pipes. Because if we take this code, the first thing we have to do is go down the branches. And on the left-hand side, we want to pass the string high into the call with the length. And so that should return 3, because the length of high with an exclamation mark is 3. And then we'll take that 3 and we'll pass it into the string. Awesome. And that should give us the string 3. That's parsing, which, brilliant. We've done it. We've gotten through the parsing, which means surely we can move on to translation. Well, translation is going to be a bunch of work. And actually, we can do something to cheat, because if you've been paying attention, we aren't actually doing anything new with our pipe operator. What we really wanted to say early on was if x is being piped into f, that's the same thing as saying f of x. Which really means if I have some syntax tree where we pipe high into the length, we're going to really think of that as being the same as the syntax tree where the high is just directly called as an argument to the length function. So we can take that brand new syntax tree node that we added to our syntax tree and get rid of it, because we don't need it. We can just totally eliminate it. Which means instead, we will do this transformation implicitly. We will take our grammar, and where previously we were constructing a pipe node, now we're going to do a little bit of code. We're going to do some code that transforms this example by taking the thing on the left-hand side and adding it to the arguments of the thing on the right-hand side. And I won't show the code here, but it's not very long, not very complicated, and it does almost exactly what I say it does. Except, oh, brilliant. We've got rid of the translation phase, because previously we were going to have to teach Python what to do with this pipe operator, now Python doesn't even need to know about it at the translation phase because it's gone. We've totally erased it, which is super nice. Something that we do run into now, that we're actually writing this code where we're doing this transformation, is that functions take in multiple arguments. And so perhaps I might want to write something like x piping into f of y. That seems something reasonable that you might want to do. Maybe you'd say, that's super unreasonable, you should throw an error. But I want to like say, maybe we actually want to consider something here. And I think there are two options. We could take that argument and put it as the first argument to the function call. We can just append it to the front. Or we can take it and add it to the last argument. And it sort of seems like there's not really an obvious choice here. You might have your own personal beliefs about, oh, I think this is like slightly nicer, this is slightly uglier. Some programming languages do it this way, some programming languages do it this way, like the first way and some of it the second way. And so at this stage, it's super important to remember that we're modifying Python here. Python's a language that's been around since the 90s, and it will probably continue to be around for many decades more. And we're sort of existing in this ecosystem already. And in particular, I want to write code that looks kind of like this, where I take an array with 1, 2, and 3 in it, and I want to pipe it into this map function, which is going to apply the stir function to each of the elements of the array. That seems super nice to me. The map function is a built-in function in Python, and it takes the list as the second argument, which means that I want to turn this thing with the pipe into this example on the right, where the brackets, where the list appears as the second argument. So for those reasons, I've chosen the second option. But you might have a bunch of beliefs about why it should be the other way around, like making sure that things get evaluated in the right order for side effects. And these are the sorts of design considerations that go into designing programming language features. What's going to be intuitive for users who want to use your code? Now, I've kept you waiting long enough. I'm going to do an extremely brief demo here. I have a custom build of Python, and the example that we had from before was hi, and we're going to pipe that into the len, and we want to check that that's equal to 3, right? Look good? And this should be true. Brilliant. Fantastic. Something slightly more complicated. We will want to do the map stir, and some of you will remember that map returns a map object, so that's not going to be very helpful if you want to print it straight out. So I'm going to turn this back into a list by piping it into another list. Oh, I've got 2 of them. Thanks, guys. Love your work. And there we go. We have an array with 3 strings in there. Awesome. Okay. So that's Python. But before we end, there are some final notes that I do want to touch on. And the first is that Python, as I've alluded to earlier, exists in an ecosystem. There's all this tooling around the programming language of Python. Like we have the Python package index, which is just a bunch of Python packages that people can use by installing them on their computers. There's static type checking for Python in the MyPy, and some of you might want your Python code to go fast, so you might use something like PyPy. And perhaps you have editor extensions and whatnot. And there are so many of those, I didn't want to put them all on here. And you might be wondering, how well does Python work with these extensions and these sort of environment tools? And the answer is, some of them works flawlessly, works great. A bunch of packages that might use the Python abstract syntax tree, which, remember, we haven't changed because we got rid of pipes, those will continue to work just fine. And in particular, MyPy, if you're doing static typing, uses the inbuilt Python syntax parser. So it'll just work out of the box, which is really nice. PyPy, on the other hand, and someone can correct me if I'm wrong, uses a somewhat custom parser, and same with a bunch of the editor tooling. It really varies from tool to tool, and they may not work quite as well. They may throw weird errors when they encounter the pipe, because they don't know what the pipe means. Now, some of you may remember way back when I said I want to be able to submit my university assignments using Python, but I've got Python on my computer. It's not on anyone else's computer. So are we back where we started? Someone's got to mark these assignments and they don't have my programming language. Well, it turns out that we can use the AST stands for Abstract Syntax Tree, it's just the acronym, to do a little bit of magic to get rid of our pipes. So Python knows how to parse our code by using the ast.parse function, and we can take in some code with pipes. Then we can use the unparse function, because Python knows how to print the syntax trees back out. And because it has no idea what a pipe means, it'll just print it out like normal. Now, we do get rid of comments when we do this, which maybe that's a little bit undesirable, but for my use cases, this is fine, and this is obviously something that you can think about. But you could totally use this to ship code that you wanted to, and you could have the... Awesome. So some of you may be really wondering, hey, Alex, this is like the coolest programming feature that I've seen in like my entire lifetime as a programmer. Why isn't this already in Python? And I'll give like a half-complete answer to that, but you can come and talk to me later more, which is that some people have already been suggesting this, and here are a couple of like forum threads on the Python Ideas forum where people have specifically asked for this exact operator, and there are other places where this exists too. And so far, the progress on them has like kind of stalled. There's a chance that one day some momentum may pick up on these again. They haven't been outright rejected, but it's like not super clear that we're going to be seeing this in Python anytime soon for a bunch of reasons. Most notably, you have to think really hard before you change the Python programming language. It's used by so many people around the world, from education to like industry, and if you're going to make a change, you're going to be impacting how people are writing code forever. Now, just because some mistakes maybe were made in the language features in the past doesn't mean that we want to keep on just adding stuff to the language. We want to be considering the changes that we make really carefully before we do. Now, finally, if some of you are thinking, I didn't know that either programming languages were sort of like this interpretable or this interesting, or I actually want to learn way more about how this sort of stuff works, where can I go? Well, I have two recommendations. The first is a book by Bob Nystrom called Crafting Interpreters. It's the book that I learned how to make interpreters from, and I think it's super approachable if you've never worked with programming languages before. Now, it's not in Python. There's a bit in Java and there's a bit in C, but I think it would still be very interesting to anyone in the audience who wants to learn more down that vein. Now, alternatively, if you want to do some real Python development on the real Python language, and what I've done here has been a little bit simplified to make things easier both for me and for you, but all the actual documentation and code styles and recommendations are very helpfully documented in the Python Developers Guide. So if you wanted to be able to contribute to the language yourself, that is the source that I would refer you to. And with all of that said, thank you very much. I now have some time for questions, I believe.